All right, so it is Berkeley time, so we can get ahead and get started. Aryan, do you have any logistical stuff you would like to announce?
April 3 is going to be out sometime in the next hour or two. That's it.
All right, so sorry, we have a question in the back.
Yeah, there should be.
Lecture 14.
Oh, we will get those on as soon as possible.
Okay. Thank you.
All right, sounds good. So most of you guys will not know who I am. My name is Soham. I am not officially affiliated with the decal this semester. Just truthfully speaking, I am a senior member in MLab, and my main kind of academic interests are high dimensional statistics and designing more computationally efficient estimators. So lots of probability stuff. However, today we'll be talking about variational autoencoders, which I personally find to be very interesting because they use some very nice ideas from probability, very nice ideas from information theory, and they all come together to get like a very solidly practical and usable model. So before I go too far into it, let me just do a straw poll. How many people in this room have taken CS70 or some equivalent introduction into probability? Okay, so roughly half the room. Of the remaining half, if I use the word like distribution or density, are those kind of familiar terms or are those unfamiliar? Familiar or unfamiliar? Okay, familiar? Okay, so if at any point I use some piece of mathematical jargon that you are not familiar with, please feel free to stop me and I can like go into some of the kind of like ideas behind the math. I will be focusing primarily on intuitive understanding. We'll be going into the mathematics only to see how the loss function is constructed to kind of like map our intuitive understanding onto our actual machine learning objective. All right, so today we'll be talking about variational autoencoders, but variational autoencoders are a bit of a tricky subject. So in order to build up into them, I'll talk about two different models along the way. First, I'll be talking about autoencoders, and then I'll be talking about latent variable models. These two different sets of models will look very different. They'll look like, you'll see them and you're like, why are they in the same lecture? The reason they're in the same lecture is because when we discuss variational autoencoders, we'll see ideas from both of them combined in a very kind of nice way. So before we talk too much about autoencoders, let's talk about JPEG. So how many people here are familiar with JPEG? I was really hoping everybody's hands would go up. So JPEG is an image format. Out of curiosity, does anybody here know some of the differences between the JPEG image format and the PNG image format? Yes, in the back.
You can save an image and save that in loses some of the
Oh, the transparency one is very interesting. I did not know that. But yes, just for the recording, some of the pertinent differences between JPEG and PNG is that JPEG is a lossy image format, meaning that the actual pixels that are captured by your camera, not all of them will be saved whenever you use JPEG. If you use PNG, it'll still do a little bit of compression, but like all those pixels will be saved. All right. So the basic idea behind JPEG is that sometimes you want to optimize for space, right? Like you are taking a bunch of photos on your phone. You might want to compress them in order to reduce the amount of like storage it takes on your phone, and maybe to reduce the amount of bandwidth you have to use whenever you're sending photos over the internet. So it's useful to be able to compress things. So the way that JPEG accomplishes this, or rather, the JPEG algorithm is designed to compress things very efficiently by potentially losing some information. So on the slides, you have visualized JPEG at 3 different levels of compression. So you can see at the first 2 levels, you can very clearly understand what the picture is, even though you're potentially cutting out a large amount of information in the terms of number of bytes, but visually it's still obvious what that cat is. At the furthest level, you can see, okay, if you tune too far in the other direction, where you throw away too much information, then you introduce artifacts that might make the JPEG harder to parse. So the reason I'm discussing data is because, yes, it saves space, it's useful for the network, and I wanted to introduce this idea that compression can be a lossy process. You can throw away information, and you might still get a representation that's good enough. Why is that a useful idea? I'll get into this in further slides, but it turns out that compression, in order to have a very good compression algorithm, you have to have a very solid understanding of your problem domain. And once you have a solid understanding of your problem domain, that means you have learned something. So I will posit in future slides that compression is actually a mechanism for learning. So let me give some more details to back up that claim. So how does JPEG actually work? So there's a few fundamental assumptions we make. The first assumption is that nearby pixels are related. Okay, so if I take an image of this room right now, suppose that I'm looking at a chair. One pixel is brown, it is very likely that the adjacent pixels are also brown. As a result, fine-grained features are usually not so important. What do I mean by that? So I'm saying, okay, you might be interested in, as a human, understanding the differences between patches of 10 by 10 like blocks of pixels, because those 10 by 10 blocks are more likely to correspond to different objects. But as a human, you are going to be less interested in the pixel-to-pixel deviations. You're not going to care that this pixel is 1% brighter than the pixel to the right of it. If I understood the syllabus for this course correctly, I believe that you guys just came out of a unit on CNNs. Is that correct? That was a while ago. So can somebody connect how these ideas of like ignoring fine-grained features relate to convolutional kernels?
In the same way that when you have a kernel run over an image, what you produce is a smaller version of what you just ran the kernel over. So with like looking for an average or looking for a max, you somehow compress the information from the previous layer to a smaller layer, smaller.
Exactly. So the basic idea is that in convolutional kernels, you're applying some aggregation operation on nearby pixels because you know that they're going to correspond to probably the same object in the real scene. So you can just combine the information from them. So the way this is leveraged in JPEG is it actually takes a Fourier decomposition of your image. So Fourier series is something you might see if you take a class like EEC16B or EE120. We have lots of classes on signals. So what you do is you treat the image as a two-dimensional signal, then you write it in a corresponding Fourier basis, and you throw out the high-frequency components. Why do we throw the high-frequency components? Because the high-frequency components are the ones that correspond to changes from pixel to pixel, while the low-frequency components will be the ones that are like changes from the right half of the image to the left half of the image. Normally, high-frequency stuff is less important. You can throw that information out, and as a result, you can get a more compressed representation. So why did I spend so long talking about JPEG? The reason I spent so long talking about JPEG is because here we're leveraging some understanding we have about images. We have the understanding that in real kind of images, you don't care about pixel-to-pixel differences. And we're using that to design a better compression algorithm. So now here's a question for you guys to think about. What if we had a compression algorithm only for cats? So instead of taking the space of all images, remember JPEG is a general purpose algorithm. You can take any image and apply the JPEG algorithm to it. Suppose that you only had a data set of cats and you wanted to build a specialized image compression software in order to compress these images of cats. My claim is that if you were to do this very effectively, very efficiently, then you would probably have to gain an understanding of how cats look like. So let me just give a high-level example. Suppose I told you that I have a short-haired black cat. You probably already have a picture in your mind of what that cat looks like, because you know what cats look like, you know what black is, you know what short hair is. So as a result, I've communicated a very small number of bits of information. I've only said a few words, but you have a full image in your mind, which is like a very high number of bits. So somehow, because you have so much background context on how cats look like, you're able to take a very sparse encoding and reconstruct a much higher dimensional signal from that, which is a really amazing thing. And that is something that we want to train our algorithms to do. Before I go forward into the actual like modern approaches to this, I just wanted to highlight this one classical example. So out of curiosity, have people here taken 16B? Anybody? Do they still cover PCA in 16B? Okay, so in some semesters they might, in some semesters they won't. I do believe this is covered in EECS 127. So you'll see that the contents of this decal, we don't explicitly require like any of the EECS courses, but like, you know, this whole space of machine learning is an interconnected web. So you're going to build off different ideas from different fields within the space. So this is an approach called eigenfaces. So this is from the 80s. It's quite old. Basically, what they did is they were trying to understand how human faces were structured. Why? Because they wanted to build a facial recognition software. So the way they approached this is they took a bunch of different images of faces. They centered them and cropped them all in the same way. Then they tried to construct a linear basis for that space of faces. And they did so by like doing some low rank projection. The exact technique is called principal components analysis, if you would want to look it up later. So people were thinking in the past that if you were able to get a succinct representation of your like data set, then that means that you must have some like, you have good features that represent some like underlying reality of the data set. So here you actually see visualized the different things that are projecting onto you. And you see that these different images might be highlighting parts of the mouth or highlighting parts of the nose to say like, oh, this feature will correspond to like, does this person have a very large nose or something like that? So now let's go into the actual autoencoder model. I've been talking very abstractly so far about compression being a good way of like learning structure. Let's see how autoencoders actually accomplish this. So this is our neural network structure. You can imagine that each of these layers are like a convolutional or a convolutional or deconvolutional layer. And you see importantly that the middle layers are smaller than the outermost layers. The idea here is that the first few layers will compress the image down into just a few channels. And the second half of the network will take the few channels and decompress it back to the original image. So in words, we are having a series of layers that shrink down to a bottleneck. And then we have from the bottleneck another series of layers that produce something of the original size of the image. The way we train this is we train this using a reconstruction loss. Reconstruction loss, it says that you take the input, you take the output, you look at how different they are. Typically, you just use like square difference. You just like take the pixel values, you do the square difference, you sum them up, and you say, was the image that I reconstructed similar or different from the original image? The more similar it is, the better loss it gets. Okay, now let's go get some intuition. I'm showing that the bottleneck layer here, the red layer that's marked code, I'm stating that it has to be pretty small compared to the number of dimensions in the original input image, and pretty small compared to the number of sample points you have. Can somebody give some intuition for why these might be useful kind of criteria to have, or like useful constraints to impose on our architecture? Yes.
Well, we know that there are some inputs that are just hypothetical to like the base, and we know that, well, we're trying to get a smaller representation of inputs, so let's try to make the focus.
Exactly. So what we're doing is that we're saying the information in the original image, I think a lot of it is redundant. So whenever you have redundancies, this means that there should be a way to compress it. So what you're doing is you're constraining your bottleneck layer to be a lot smaller than your other layers in order to force your network to learn to discard and then reconstruct those redundancies. As like a challenge question for you guys, why do we have an encoder and then a decoder? Why don't we just like have an encoder and train that without a decoder?
You want to reproduce what we took in input?
Exactly. It's like if you just had the encoder, there's no loss function you would train, right? Like how would you tell if a certain code is good or not? There are ways to do this if you use like contrastive losses. We won't go into that right now. But the basic idea here is that you want to judge if your encoding is successful by saying, can you decode from it? So that's why we train both the encoder and the decoder together. So to see, can you reconstruct the images that you pass in? All right. So we don't actually normally use autoencoders by themselves. Normally we impose like some sparsity requirements on the bottleneck layer, or we impose that maybe you add some noise to the output of the bottleneck layer and see if the decoder can decode that. Those are called sparse autoencoders and denoising autoencoders. Those are both very useful things. We won't go too much further into them because they're not super related to variational autoencoders. But actually, if you look up the autoencoder literature, both of these things are very interesting to look at. Basically, sparse autoencoders try to constrain it so that your features will, only a few features will be active at the same time in your after the output of your bottleneck layer. So that can sometimes help enforce interpretability. And denoising autoencoders can be used for tasks like super resolution. So maybe you pass in a low resolution image and you want it to output a higher resolution version of that image. So doing like interpolation in the right way. Those are like autoencoders can be useful for tasks like that. Okay. So yeah. This question, what do we want from a code? Potentially confusing. I might reword this. But the basic idea that I wanted to get at is that you have your encoder and decoder. You want your output of the encoder to satisfy some properties. One of them is that if you're using this for the purpose of image generation, then you want it so that any possible output of your bottleneck can be decoded. So what do I mean by this? Well, technically, the autoencoder structure only enforces that the things in your data set, when you encode them, will get something that is able to be decoded to the original. It's not saying that if you took a random point in the space of possible code words, that would also decode nicely. So that's like one kind of like undesirable property of autoencoders. It's not able to generate new images in like a very sane way. The other one is that frequently we want to be able to interpolate between different code words. So what that means is that if you encode two different images and you take the average of the two codes and then decode it, you'd want something that looks like the average of the two images. So maybe one image is an image of like a poodle and another image is a image of like a Labrador. If you would want it so that if you encode those two things, take the average and then decode it, you get a Labradoodle, or like some dog that looks halfway between a poodle and a Labrador. You would not want it to just produce some random static. So those are two kind of issues that autoencoders run into. So let me take a pause here because I've been talking for a while. Do people have any questions on like autoencoders or about these kind of problems we have with autoencoders?
Are autoencoders useful for the whole, not just images, but also language or other text models?
Yeah, exactly. So we are calling this decal deep learning for visual data. Some of the techniques we describe are going to be really finely tuned for vision. So stuff like CNNs, it can be used in other places, but like it was designed for visual data. I would not say that autoencoders fall into the same kind of regime. You can use autoencoders on pretty much any data, and then you'll probably get something sensible out of it. So yeah, like a very solid example is I think phone companies actually use autoencoders to compress like human speech in order to like reduce the number of bits they have to send over the wire. So it's just like there's like other kind of like use cases there. All right. So we spent some time talking about autoencoders. Let us talk about a different class of models called latent variable models. You might also hear these called like Bayesian models or Bayes models. If you take CS188, they have an entire unit on Bayes nets, which is a very closely related idea. So before I was talking about autoencoders, they're used for like, essentially you can think of them as like some mechanism for compressing your data. Now I'm shifting gears to a slightly different problem. I'm considering the problem of image generation. So your input to this problem is a data set of some images from some distribution. For concreteness, just imagine this to be the space of possible cat images. And the output of your model should be new images from the same distribution. So I give you, 1,000 different images of cats. I want you to show me a cat I've never seen before. This is an example of unsupervised learning. I'm not actually giving any labels to the data. So it's not like saying I'm training a classifier to discriminate between cat and dog images. Instead, I'm saying I'm given some data that follows like some distribution or some pattern. I want to learn that pattern and generate new data. All right. Actually, I believe, the reason I had that bullet point was because I believe the rest of the decal will be largely focused on unsupervised learning and how to use generative models. Generative modeling has received like a huge amount of attention over the past couple of years. There's been models like ChatGPT, like DALL-E from OpenAI. They are all generative models at heart. So like over the next couple of weeks, we'll be discussing some of the techniques that are used to build these models. All right. Now going back to this problem, there's a couple of images you can get with generative AI. One of them is the problem of memorization. So I give you a data set of 1,000 cats. I'm like, okay, show me an image of a new cat. How do you prevent it from just showing me one of the 1,000 that you fed it, right? You want it to be a truly novel example. You don't want it to just be just an example it regurgitates from the things it's already seen. So whenever we design our models, we'll have to keep that in mind. The other thing we'll have to keep in mind is something called mode collapse. We want to make sure that each time we run the model and say, give me a new image of a cat, it really does give a new image of a cat. One potential issue is that maybe you train a model, you say, give me a new cat, it gives you a new cat, you're very happy. Then you say, give me a new cat again, and maybe it gives you the exact same image. That's another kind of like degeneracy we want to avoid. So those two things are not explicitly tied to this lecture in particular. The problems of memorization and mode collapse are things that you're going to see again and again addressed throughout the lectures on generative AI. So like this Wednesday's lecture, I think is on GANs, correct? So whenever we talk about GANs, they'll like talk a lot about mode collapse. But these are just like some terms you should know, like how to frame your thinking for approaching this problem. Okay, so now let's actually talk about the model. So whenever we say we have a latent variable model, we're saying we're going to generate our data in two steps. First, we sample some random variable we call a latent. So that's just some vector. Then, given the vector, we pass it through a different model, and we generate the data conditioned on that latent. So the way I like to think of this is that suppose that you're trying to understand faces, you can kind of think of the latent as like the genes or the genetics, and the actual data as like the faces. So you don't actually observe people's genetics whenever you go on a day-to-day basis. You don't like say like, oh, I meet someone, like what is your like genome? Well, what you can do is like you see a bunch of different images, and then in your head you construct like a series of features that are useful. Being like, oh, this person has like a very high brow, or like, oh, this person has like a very I don't know, a very like sharp nose or something like that. So as you view different faces, you construct a set of like useful features. You'll encode this as your latent, and then from that, whenever you like fix a latency, you can generate some data. All right. The other thing I want to mention is that we will enforce that the latent is lower dimensional than the actual data that you generate. The reason this is very important is because if the latent is the same like dimensionality, then you can run into problems with like memorization or overfitting. Essentially, we're saying, again, this is like a common theme in machine learning. The space of like the actual dimension of the signals that you get, if you get like an image that's like 100 pixels by 100 pixels by 3 color channels, that's like 30,000 different values. That is way higher dimensional than the actual dimension of the underlying space it describes. So like describing cats, you only have to describe like a few different parameters, like the length of its legs, the length of its hair, the color it has. So like by enforcing that our latent is much lower dimensional than our value x, and then we just assume that our mapping is going to be a continuous mapping, we're going to get that the output of our model will like lie in like a kind of lower dimensional space than the full space that x can live in. As an aside, here we're showing two-step modeling where you first sample Z and then you generate X given Z. You might be asking yourself, why do you do it in two steps? It is possible to generate X directly. A typical approach is like using auto regression or something like that, where you like sample like each pixel in your image one at a time. I won't go too far into that. That's just like a different kind of track of machine learning you can go into. The final thing I wanted to mention before going into more technical details is the log likelihood loss. So out of curiosity, how many people here have seen log likelihood? So there's like a couple of people. The basic idea is that you're saying that you have this model that is parameterized by some theta. These theta corresponds to your model weights in a machine learning, in a deep learning model. So you want to fit your model to your data. You want to say like, I want to find the model weights that most effectively captures the data that we observed. So how do you measure this? You need some loss function, right? So a typical loss function is the log likelihood. So before we go into log likelihood, let me just define likelihood. Likelihood is just saying, if I fix these model weights and then I run our generative process, what is the probability of actually observing our data set? We want this number to be high because then it means that the way we're modeling it corresponds to the actual data that we observed. So that's why I'm saying that you can use as your objective p theta of x1 through xn. And if we further assume that our samples are independent, you can just write this as a product over those different probabilities. On the other hand, products don't really play nicely with gradients. If you imagine trying to take a gradient of this expression with respect to theta, then you'll have to do product rule. That becomes very messy. Also, products are very prone to numerical issues. If you imagine you're taking the product of 100 different numbers that are each like less than 1/2, then it's possible that you get like some very tiny things, and you get like float underflow. So yeah, likelihood is not very useful as a loss function. So we typically take the log likelihood. So remember that maximizing the log of a function is like the value of theta that does the optimal for that will still be the same value of theta that maximizes the likelihood. But the difference here is that now you've turned that product into a sum, and now sums are like much nicer to work with gradients. Let me just pause here. Do people have a question about why we use the log likelihood loss or about our generative modeling framework? All right. So the way that you train a latent variable model is you want to maximize your log likelihood, as I mentioned in the previous slide. So how do you do this? Well, we said that we generated Z, and then using our model weights, we generate X given Z. So this log likelihood, that's going to be some marginal distribution. So you can write it as you sum over the possible Z's that you can see. You like say, what is the prior probability of generating that Z? And then once you pass it through your model, what's the probability of observing that given the Z that you get? So do people like understand how this computation goes? This is the chain rule of probability. Fantastic.
So sorry, we're running the likelihood probability and then we're running the log likelihood over that original probability?
Yeah, so what we're trying to say is like, okay, this is your model. So you sample Z from some distribution. We call it our prior. Or I'm not going to give it a name. Let's just call it P. Then given Z, you generate some value X. So a typical example might be like you sample some like Gaussian distribution, then you feed it through your model, and then that gives you some X. So like the point of this like Z is just saying give the model some randomness to start with, and given that randomness, it will start producing some images. So because this is random, it'll produce a new image every time. All right. So our goal here is we want to compute the maximum over theta of the marginal distribution for X. But recall that this marginal distribution is given by a summation over Z of the choice. Right? So you have to consider all the possible different things that your all the possible z's that can be generated, and they will each contribute some probability of producing that x. So this is why we get the summation over z. And then you can further decompose this as the summation over z of your prior probability times x given that z. And sorry, here I'm just doing it for one sample point. And typically you'd also want to take the log of this. Yeah. Does that answer your question at all?
I'm gonna have to Google a lot of this later, but given a random noise that leads to X, we take the probability that that random noise led to X, and then we get the probability of that probability. Is that about right?
The probability of that probability.
No?
Um,
Tell you what, after your lecture, if you can
Okay.
like, send me some links or.
Sounds good, sounds good. Yeah, so throughout this lecture, I'll be talking a little bit about some like conditional probability stuff that will be exposed, like of course, like CS70. I will also send out some links if that will be helpful for people, just as a refresher. Yes, another question?
I'm seeing here that like if the sum over z and that if you use Monte Carlo with further z, but the problem like if z is continuous, I assume that would be difficult.
Yep.
And you know, like numerical stability and estimating variables is kind of hard. So there.
You are correct. There are some numerical issues with here. I'm gonna hand wave those because we're gonna see in a future slide like what we do instead. Yeah, like actually a major issue with this approach is that for most values of z, the probability x given that z will be very low. So like for most kind of values of your latency, you won't expect to see that image given that latent. So actually most values of z that you sample using the Monte Carlo estimate will not be important. So that's actually why people use something called importance sampling. I won't go into that in this lecture, but that's going to be a useful word for you to Google if you have some free time. Let me just write it here. Can you read that? You should also search up IWAE. This stands for importance weighted autoencoder. So this kind of addresses some of the numerical issues you were talking about. All right. So yes, just going out into a bit more detail on that. So the disadvantages here is that Z might be high dimensional. So you can imagine that if you're generating some random noise, suppose that it's like some kind of like 100 different coin flips. So that's only 100 bits long, but in terms of like the number of things you would have to sum over, that's 2 to the 100 different values. So that summation over all the possible Z over here may not be tractable. The other thing is that even if you use Monte Carlo, you might not get a good approximation for the gradient, and that's because some of the issues that we talked about right now with importance sampling. Not all of the Z's will contribute a non-negligible contribution to that summation. So that's very annoying. Another kind of annoyance is that you can't get Z given X very easily. Remember, we have the probability of Z. We said that Z was like some Gaussian or something like that. And we said that we could take X given Z. We can pass it through a neural network. Doing the reverse process of getting Z given X, that requires Bayes' rule, and that'll also be an expensive computation. The reason that's so annoying is that if you want to do something like interpolation, where you are given some image and you're saying, oh, what is its latence? Let me like kind of interpret what the latence means. Then that will be very tricky. Also, I'm so sorry. I don't think I formally defined what a latence was. And that's because latents don't really have a formal definition. Whenever I say the word latent, I'm referring to that Z over there. It's a thing you first generate, then you pass through your likelihood model, and that'll give you the data that you observe. It's basically saying like, this is like the hidden part. This is like the hidden features that we're learning, but we don't directly observe. All right. Yeah, so one of the issues with doing it this way is that we require the summation over Z. So a different approach that you can do to model this log likelihood objective is by rearranging Bayes' theorem. So once you rearrange Bayes' theorem, you get that equation. And what you can do is you can say, okay, X given Z is nice because that's just our neural network. And P of Z is also nice because I just said it's going to be a Gaussian or something. You can choose what the probability distribution over Z is. So typically what you do instead is you say, okay, the P of Z given X, that's the tricky part. So how about we just replace that with like a nicer class of distributions instead of the full complexity of like the full posterior. So you approximate that P of theta of Z given X with some like new kind of neural network. So I'm going to call that Q sub phi. And if your new set of distributions is large enough, then this will hopefully give you a good approximation. The reason this is better is because now you can start using the elbow loss. Sorry, before I can talk about elbow, I have to talk about KL divergence. I won't go super far here. It's just that KL divergence is a standard way of measuring the distance between two distributions. It's saying how different is this probability distribution from this other probability distribution. There's an interpretation from information theory, which basically says if you encode values from true distribution P, but you use an encoder optimized for Q, how many extra bits will you need per symbol? That's basically like where this idea came from. But I think for you guys as machine learning practitioners, you should just think of this as the canonical example of a loss that like measures the distance between two distributions. In the same way that, you know, squared error loss is the canonical example of a loss between 2 points in like in Euclidean space, and how cross entropy loss is a canonical example of a loss used for categorical data. This is just like one of those things you should put into your bag of tricks for like, as these are the things you can put into your loss function. And just as a theorem, the KL divergence is always non-negative, except in the case where, it's always non-negative, and it's only 0 whenever the two distributions are the same. Okay, finally, we're getting to the elbow bounds, the elbow loss. This is something that Aryan asked me to include because I believe that, like some of the derivations here will be useful if you guys go further into latent variable modeling. So actually, for interest of time, I won't go through the full steps here, but the basic idea is you consider the KL divergence between your approximating distribution, Q phi, and your actual posterior, P theta of Z given X. And once you like expand that out, you do some steps, you can rearrange, then you get your log odds, your log likelihood is lower bounded by a certain expectation. And this is the actual expectation that we optimize. Yeah, for simplicity, I'll skip this slide. Basically, instead of the actual log likelihood is computationally intractable to do. But once you do these manipulations and you get a lower bound, that gives you something that's easier to estimate and easier to do Monte Carlo sampling on. Finally, it makes sense to do the maximum of something that's a lower bound, because remember, if your lower bound is something, then maximizing that means that you found a point that must have a pretty good real objective, even though you're just optimizing lower bound instead. All right. Sorry, so that was like a lot of mathematics in like a pretty short period of time. But now I want to bring the ideas of latent variable models together with ideas from autoencoding. So the intuitions from those two different domains will come together into this model. So the basic idea behind VAEs is you want to be able to associate your distribution over the latency with your data points in a principled way. And in doing so, you'll actually impose some structure on the latent space. So this is what the model actually looks like. The model will take in some input image, you pass it through an encoder, and this will get you a couple of numbers. It'll get you a mean and a standard deviation. You'll pass in that mean and standard deviation to generate a normal distribution. You sample an example from that normal distribution. Then you pass it through the decoder, and then you use that to reconstruct the original image. The loss that we use to train this will be a combination of our reconstruction loss that we saw earlier in the slide deck for autoencoders. This is basically penalizing the network from not being able to decode correctly. if the decoding is very far away from the original image, then that will cause the reconstruction error to be high. So that's one contribution or loss. The other contribution or loss is some regularization term that is forcing these outputs of the encoder. Remember, the encoder is outputting a normal distribution. It's forcing the outputs of the encoder to be close to a standard normal. So the reason this is useful, I'll go into in the later slide. So yeah, just like putting this in words, instead of outputting a single latent from our encoder, we'll output a Gaussian distribution, sample something from that, and then pass that through the decoder. So we train with a reconstruction loss and with a regularization term that is normalizing towards a Gaussian. So the reason this is useful is because it gives us structured latents in latent space. So for a regular autoencoder, only the outputs of the encoder can be correctly decoded. So yeah, like if you just sample like a random latent, it's not necessarily true that's going to be able to decode it correctly. On the other hand, whenever we enforce that out of our encoder, we get parameters to a distribution, and then we do random sampling from that, we're enforcing that nearby points in latent space have to decode to similar things in data space. That's a very important point. Do people have like any questions about like how that's occurring? Why is it that using the probabilistic encoding here causes us to have a nicer structured latent space?
Is it because you're taking, you're trying to find the probability of the random input that's actually useful?
Probably. I think that's like a good kind of like, we're getting somewhere. We're getting somewhere. So basically, remember this is how standard encoders work. So for a standard autoencoder, you compute some neural network encoder on your input, and then you pass that through a decoder. So what can happen here? Suppose that you have 3 sample points, x1, in some space, you have 3 sample points, x1, x2, and x3. And then you pass it through the encoder. And maybe the encoder just outputs one real number. Perhaps it maps x1 to z1, it maps x2 to z2, and it maps x3 to z3. Then what our decoder can do is it can just memorize those 3 locations. And it'll say, if you're close to here, I'm going to output x1. If you're close to here, I'm going to output x3. And if you're close to here, I'll output x2. Now, suppose that you wanted to generate like a new kind of like random image. And you try taking this point over here. You try taking z4. There's no guarantee that whenever you pass it through the decoder, you get something sensible. This can like be anywhere in the space. It's not likely to actually be interpolating between these different things over here. Not the problem. So the way we fix this with variational autoencoders is that we say that our encoding will give us a mean and standard deviation of some Gaussian distribution. Then we sample from that Gaussian distribution. And then we decode. So why is that useful? Now let's take the same picture. We have our different sample points. Now what happens? So suppose that x1, it doesn't get mapped exactly to z. Sorry, it doesn't get mapped to 1z. It gets mapped to a distribution over z's. So let's call that distribution z1. Then x2 gets mapped to a different distribution. And then x3 also gets mapped to a different distribution. Now suppose that you consider as like some point over here and you try running it through the decoder. So what will the network see? The network will see, okay, this point over here, it could have been generated from the distribution Z1, or it could have been generated from the distribution for Z3. But it has to produce a good loss on both of those cases. So what it'll do is it'll actually try to produce something that will get decent loss against input X1 or against X3. So actually what will happen is it'll produce something in the middle. So this is like an amazing fact. The fact that you've switched from this deterministic encoding to a probabilistic encoding means that things in the middle, in between two different latents, if you just interpolate between them, you'll end up something in your data space that are in the middle as well. So we see this visualized on the board. So whenever you just train a standard whenever you train a standard autoencoder, you see the points. You can imagine that this is like an autoencoder for MNIST or like some data set that's like for digits. You can see that the different points, even the ones in the similar classes, just get flung off to different parts of the latent space. And that's because there's nothing forcing the similar points to stay together here. On the other hand, whenever using a variational autoencoder, the fact that we're sampling from a distribution means that you're forcing nearby points in latent space to decode the similar things. So this will actually influence the model to put like related points in the original space and have them produce like similar distributions. So you get that nice clustering over here. Yes, you had a question.
Is it possible interpretation of this to say by enforcing something like continuity in latent space and therefore like exploiting the fact that the neural network is mostly continuous, we like also say that projection on X, in this case of X, also has to be continuous.
So what you're saying is a true fact. The fact that we're assuming that our models are all continuous doesn't force continuity. Continuity, unfortunately, is not a very strong condition though. So like technically, even for the standard autoencoder, all this stuff is continuous, right? So you're not kind of like bringing up your latent points and your latents into a nice cluster. Okay, granted, if I move like an infinitesimal step away, then it is true that your output would only move a small amount. But I'm considering non-trivial changes to your latents. Will not necessarily map to non-trivial changes to your points here. The idea that's like so powerful behind variational autoencoders is that you replace the generation of a single latent with an entire distribution. And the idea is that these distributions will have overlap, right? We also have a regularizer to enforce that these variances of the distributions are not too low. Because the variance is not too low, it's forcing these things to have non-trivial overlap. Whenever there's overlap, you'll have to be able to produce a decoding that can produce good loss for either of the two cases. And in doing so, you're forcing it to have like some good interpolation between the different latents. All right. And then finally, the way you actually use this model to generate new images is, remember, we regularized. In this loss, we're regularizing the distributions produced from each of these encodings to be close to a standard normal. So this is trying to like force it so that none of these like peaks collapse to a point. You don't want that to get too small. You also don't want your means to get too large, because if your means are very large, then maybe all the different distributions will be far apart. By forcing them to be clumped together, this is enforcing a non-trivial overlap between the different peaks. And in doing so, you're enforcing some measure of like interpolation between those different points in the original space. So if you actually want to sample from this, what you do is you just like sample from a standard normal and you pass that through your decoder, and that'll give you a new image. Finally, the advantage of VAEs over alternate modeling for generative models is that these latents are pretty interpretable. Like if you actually like, you can do some visualization tricks on the latent space to see like, oh, this part of the latent space is encoding the idea of cats, while this part of the latent space is encoding the idea of dogs. Future lectures will focus on other generative models, but those will have like kind of less interpretable latents. All right, I'll be running 1 minute over time, but I just want to kind of do a quick recap. So we've seen three things today. We've seen autoencoders. We've seen that they are able to take some data, they compress it, and then they decompress it. And doing so, they have to learn some structure of the data. You train it using reconstruction loss by saying how far is the input from the output. We have seen latent variable models. What latent variable models do is they start with some noise, they pass it through a model, and you see how well you can like fit your data set to that. That's trained with log likelihood loss, and we saw that you could further make this more numerically efficient by using the elbow approximation. Finally, we saw variational autoencoders. It combines the two ideas. How is it combining the two ideas? First, it's using the idea of autoencoding to have an encoder and a decoder, and you've trained using reconstruction loss. But on top of that, it says, oh, the idea of taking noise and using that to map to some data points is also very useful. So instead of just doing single point encodings, it does probabilistic encodings. So here we don't output a single point from the encoder, you output a distribution. So that distribution, this decoder, has a very similar role to the latent variable models we saw earlier today. So this model combines the ideas from the two of them and actually produces some very nice results, which is why we're teaching it to you today. Okay, that's all I have time for. Do I have any questions? Fantastic. That's if you have any further things, you can talk to me at the front. Oh, I pulled up the wrong thing. I'm so sorry. Okay, so for attendance, you can click here.
Hey everybody, this is Soham 2.0, just recording in the future because part of my lecture was on the board and that was not really captured by our recording. So yeah, I just wanted to recreate the diagrams I drew for everybody in the in-person lecture for you guys, so you could review it at home. Basically, the point I was trying to make was saying, why does probabilistic encoding enforce structured latents? So that's the question we have. So recall that in our standard autoencoder setup, what we have is we have a bunch of different points in our original space. So remember that if you're passing in images, those are some very, very high dimensional things. Those are like tens of thousands of different dimensions. I'll just draw a cube for simplicity. So you have these different points living up that are corresponding to your images. They live in the data space. Then you pass it through the encoder, and then it'll output things into a lower dimensional space. So for simplicity, I'm just going to draw the low dimensional space as a line. So maybe you get that like this is Z1, this is Z2, this is Z3, this is Z4. And then finally, you have a decoder model that can go the reverse direction. So the basic idea here is that whenever you train your autoencoder, you will be able to map these different points in the data to these different points in your latent space. Now, there's nothing saying that if you were to take a new latent point, suppose that you define this new latent point, its mapping back into data space might give you garbage. There's nothing forcing it to be sensible. Now, like there was a question during the in-person lecture being like, oh, can you like kind of argue using continuity of the neural networks involved, that it has to be like somewhere reasonable? It's not super great because continuity is not a very strong condition. So just know that if you're given an autoencoder model, you're not going to be able to use its sorry, you're not going to be able to use its latents and like just generate new latents and hope to decode it to kind of new images. That's kind of like a big fault of the vanilla autoencoders. So what we instead try is we consider variational autoencoders. So let me just copy over the first part of this image because that stays the same. So the actual data looks very similar, but instead of just outputting a single point in the latent space, what we're going to do is that the variational autoencoder is forced to output distributions of points. So instead of just outputting Z1 and Z2, you'll get like these little distributions. So yeah, you can just kind of imagine that these are like little Gaussians sitting at those different locations. So why is having all these different Gaussians like better than having just single points in latent space? The basic idea is now suppose that you consider some points over here. Okay, so very similar setup to what I was describing before. If you consider some point there, you'll see that's actually between the peak for Z2 and the peak for Z3. So there's like a non-trivial probability that that point was generated from passing X1 through the encoder versus passing X3 through the encoder. So this means that the model will be forced to learn something that will have a good loss, regardless of whether it's like something that's close to X1 or something that's close to X3. So what's going to end up happening is that the model will learn to like kind of interpolate between those two things. Because like it's not entirely sure which one it is, so it wants to make sure that's able to get, kind of good score on both of those. So maybe that's not enough to really convince you that this will produce like a very sensible latent space. It's not like you could imagine that, oh, that maybe it'll just do like a pixel-wise average of like, the nearest neighbors for that point in latent space. But it turns out that whenever you actually do experiments, you get very good results. We have some pictures on our different blog posts, and you can check out our Substack. You can check out different things online, running experiments with VAEs, and you'll find that they have fantastic results whenever you sample from latent space. But yeah, this is the point I was trying to emphasize. The fact that you're doing like probabilistic stuff means that you're forcing overlap between these different distributions, which forces like kind of continuity, or like not really continuity, but you're forcing your latents to interpolate well between the different modes. Last thing I'll mention is that the reason that we need to have this like regularization term in our VAE loss, that's like KL between the output of your encoder, your encoder outputs a mean and standard deviation. You do KL divergence against a standard normal. The reason you need to have that term is because if you let your variance like grow too small, then you can have the VAE degenerate back to the AE case, like there's no overlap between these Gaussians. And then if your means get too large, then it can be driven off to different locations in latent space. So you want them to be like really close together, like these different peaks to be close together, because whenever the peaks are close together, that forces more overlap, which causes kind of the network to learn more interpolation between the different points in your distribution. And the more it can interpolate, the more kind of structure it actually recovers. Yeah, so that's all I wanted to say. Have a nice one.